In the previous session, we saw synthesis algorithm for parametric time automata addressing parametric reachability or parametric trace preservation. These algorithms, as all algorithms for parametric time automata, are very costly. So, we will here try to improve the performances using distributed algorithms. So, algorithms are costly because they require a lot of time and a lot of memory. Why? Because we do very expensive operations on polyhedra. And there is no known efficient data structure for parametric time automata. This is in contrast with on-time systems, where we can massively use BDDs, or in contrast to time automata, where we can massively use DBMs, which are very efficient in both cases. The idea to speed up the computation will be to benefit from the power of clusters. So a cluster is a large set of nodes. So a node is a computer with its own processor and its own memory. And these nodes communicate between each other over a network. It can be a local network or even a wider network. A first naive approach to distribute the EF-syn, so the reachability synthesis. Remember to synthesize valuations for which a given location is reachable or not. So the naive approach would be to handle a different subpart of the parameter domain for each of the nodes. So for example, if we have 4 computers, we could say that one of the computers will handle this green part of the parameters. So we'll try to find good valuation there. Yellow computer will try to find good valuation there, and same for the blue and the red one. How would it work? We would launch 4 computations in parallel. Okay. Maybe very quickly, this node will say, okay, my entire state space is for instance, bad if we are looking for a bad state, so all those valuations can lead to the bad state. Then this node is done. Later, the red node will say, okay, for me, almost everything is bad except this small part for which the system is safe. Then the green part maybe would say, this one is bad and this one is bad, but the rest is correct. And then much later, because it's much more difficult for the last node will synthesize this constraint, saying this part is bad, and then there are plenty of small bad parts here. But actually what happens, which makes it not so efficient, is that if we had run only one analysis on a single node, probably this big valuation set could be found with the same as this one. This one is just a small part of that one, and with the same effort, we could have synthesized all that using a single node, this blue node. So there is clearly a problem of redundant computation. And the second problem is that if we have a lot of small parts of the evaluation set for which the system is bad and it looks like that, most probably there is a lot of analysis to do there. So it means the blue node has to take much more time than the others. So it's not fair, and the performance will be bad if the analysis is more costly in some subdomains than in others. So we will choose a more elaborate approach based on the master-worker paradigm. So there will be a single master, a node, that will be deciding what the workers will do. The workers will run a hybrid algorithm, hybrid in the sense that it looks like 2 existing algorithms. It looks like the reachability synthesis, EF-syn, and the trace preservation synthesis to just explore a part of the state space that looks like a valuation that we know already. And this algorithm is called PRP, for Parametric Reachability Preservation. And it's based on integer points, meaning that we will iterate an integer point and try to find constraints that enlarge, that generalize the behavior of one integer point. So overall, in theory, we only guarantee the coverage of all integer points, so rational values may be missing. In practice, we get most of the domain and often all of it. And then the master will be responsible for gathering results and distributing reference valuations, the points, among the workers. And this actually is not an easy task. Let me show in the non-distributed setting how the PRP cartography, so PRPC, works. We start with an integer point. We compute a constraint that generalizes this integer point. And if this integer point is safe, if we can't reach the bad locations, then all those rational points are safe as well. Then we move to the next uncovered integer point, this one. We generalize it. Again, it's safe. Then we move to the next one. That one is a bad zone, meaning all those parameter evaluations may eventually reach a bad state, so they are unsafe. And we do like that until we completed our full bounded domain. So this is a non-distributed setting. Now in the master worker scheme, the workers will ask the master for a point, so an integer evaluation, will call PRP on that point, find the constraint, and send the result to the master. The master will be responsible for the smart repartition of the data between the workers, and it is not trivial at all. We've been working on different algorithms to try to be smart for this data repartition, and it's not always easy. Let me show now a distributed scheme. So we have one master, which is not depicted here, and 3 workers that will select integer points and generalize them. So let's suppose we start randomly with these 3 points. Now, let's suppose one of those nodes finishes and generates a green constraint. So it was node number 2. So then node number 2 finishes, it sends this result to the master, and it moves to another point that the master chose. Then this one, V1, finishes its computation, so it moves to another point. Then this one finishes quickly this big bad computation, moves to an uncovered point, randomly chosen. This one finishes as well, moves to another one. Finally, V1 finished, and you notice it just generated the same as the first point initially computed. So we have 2 times the same computation. Then you move there, and so on and so on and so on. I move quickly for the end. Okay. The problem is that we have redundant computations because we can't know in advance which tile, which set of evaluations will be synthesized by one node. So what happened here is very common. We had 2 different nodes synthesizing the same constraint. It's not a big problem in terms of correctness, but it is a problem in terms of speed, of efficiency. So we had redundant computations. We experienced a lot of different ways for the master to smartly send the integer points to the workers, and the most efficient distributed so far is what we call a domain decomposition scheme. So the master initially splits the parameter domain into subdomains, sends them to the workers, a bit in the spirit as the naive approach we talked in the beginning, and then when a worker has completed all of its subdomain, then the master will give it more work by splitting an existing domain and send it to the idle worker. The workers, nothing has changed. They receive the subdomain, they call PRP on all points until everything is done. Then they send the result back to the master and they ask for more work. So initially we have this 2-dimensional domain. We have 4 workers, so we just split into 4, okay? And the master will just give a part to each of them. Then if a worker has completed its whole subdomain, it asks more work to the master. The master finds a node that is not doing very well. You see that worker 1 didn't cover a lot of points. So we split this domain. Part of it goes to worker 2, and only this part remains for worker 1. Worker 1 is informed that its domain is becoming slower, so it has a bit less work to do. And so the master can dynamically balance the workload between the workers. This was implemented in the model checker imitator using the MPI paradigm, so the message passing interface. And we got in the experiments that the distributed version was up to 45 times faster using 128 than the non-distributed version. So as a conclusion, we presented a first version of distributed algorithms for parametric time automata. What remains to be done? So there is a large space for improvement. In the base case, we get 44 times faster with 128 nodes, which is very nice, but it still means that we could be, in the base case, be 128 times faster with 128 nodes. Another direction would be to do multi-core parameter synthesis. So multi-core is not the same as cluster-based. Multi-core is you have a single machine, but you have different processors, and this is not yet done, and of course, eventually, it could be combined with cluster approach. In the next sequence, we will see a bit of tool support.